EDX Core Pure complex numbers 3, modulus argument and loci, Cartesian to modulus argument form. We've already seen the benefits of using the Cartesian system xy to show the position of a point on an Eigen diagram. However, it is often more useful to use the modulus argument system r theta, where, as you can see on the diagram, the distance from the origin is r, where r is greater than 0, and the direction from the positive x-axis is theta. When measuring theta, it's important to use the principal argument, which is greater than minus pi and less than or equal to plus pi. So when converting the Cartesian xy to the modulus argument r theta, first thing we need to do is to find the modulus. So this can be called mod z, or you can simply call it r. And you can see from the diagram we can find r by doing Pythagoras on the x and y. So r equals the square root of x squared plus y squared. And again, just a reminder that r will always be a positive value. So if we want to write down the modulus of the following numbers, so the first one is 1.5, that's about there. So its modulus r would simply be 1.5. 3, 4, which is there. You can see if I just draw a little triangle there. So we've gone 3 across and 4 up. So we've gone 3 across and 4 up. The length or the modulus of that complex number must be 5. If you do Pythag on 3 and 4, you'd get 5. If you look at minus 4i, which is there, the modulus of that is 4. Notice it's not minus 4, it's positive 4. The length is positive 4. And if you look at minus 4 minus 4i, which is here, and again if you just look at this, so we've got 4 back, 4 down, and if we did Pythagoras to find the size of that complex number, we'd get r is 4 root 2. We also need to find the argument of the complex number. We need to be a little bit more careful with this one. The formula is theta equals tan minus 1 y over x. So we're looking for theta in this triangle, tan minus 1 y over x, but occasionally you'll need to plus or minus a pi. We can check whether with theta requires a plus or a minus pi or neither by sketching the point and noting its quadrant. So here, in the first quadrant, theta equals tan minus 1 y over x will give us a positive value and will give us correct angle theta. In the fourth quadrant, theta equals tan minus 1 y over x would give a negative value and the correct theta. However, in the second quadrant, tan minus 1 y over x would also give a negative value. So to make sure we're in this third quadrant, we need to add on a pi. And if in the third quadrant, tan minus 1 y over x would give a positive value. So to make sure we're not getting into the first quadrant, we need to take off a pi to get the correct angle. So care must be taken in the second and third quadrants. So if you have a go at writing down the principal argument for each of these. So the first one is 4i. So 4i there's 4i, and we can see that its argument theta would be exactly pi by 2 from the positive real axis. If we look at minus 3, now care must be taken with minus 3. There's minus 3. Remember, the principal argument is greater than minus pi and less than or equal to plus pi. So for this one, we'd quote plus pi. 3 minus 3i is there. And if we did this one as tan minus 1 minus 3 over 3, it would give us the correct answer of minus pi by 4. And minus 3 minus 3i, this is the slightly tricky one. If we just did tan minus 1 minus 3 divided by minus 3, the calculator would give you pi by 4. The calculator would think you're looking for that angle there. So in order to get the correct argument in the third quadrant, we need to take off pi. The correct answer is minus 3/4 of pi from the positive real axis. So now we're in a position to convert Cartesian to modulus argument form. We've seen that the x coordinate is r cos theta, the y coordinate is r sin theta, z in Cartesian form is just x plus iy, so we can replace x with r cos theta, we can replace y with r sin theta, and usually we take out r as a common factor to get z equals r bracket cos theta plus I sin theta. When using this modulus argument form, you need to make sure that r is a positive value. Cos theta comes first, and make sure there's a plus sign, I, and then the sin theta part of the answer. And this is called the modulus argument form, or the polar form of z. So here we've got z equals minus 1 plus root 3i, and we want the modulus argument form. So we're going from the Cartesian to the modulus argument form. So the first thing we're going to do is look for the modulus of z, or you can simply call it r, and we get that by doing Pythagoras on the components. So r is square root minus 1 squared is 1, root 3 squared is 3, r is root 4, and notice we take the positive root 2. We want the argument, so theta equals tan minus 1, the y component divided by the x component. Now it's well worth at this point just being careful and having a look at the sketch of this. So just have a look at the sketch of this complex number. So it's minus 1 plus root 3i, so it's roughly there. So if I leave it as tan minus 1 root 3 over minus 1, the calculator will give us this angle here. So in order to get the correct argument, which is this angle here, that's where theta needs to be, we need to add on a pi because we're in the second quadrant. So theta equals minus pi by 3, which is the answer your calculator would give you here, and we're going to correct it with a plus pi. So theta equals 2/3 of pi. Now we've found r and we've found theta, we can write z as its modulus r, which is 2, cosine of the principal argument, which is 2 pi by 3, plus I sine the principal argument 2 pi by 3. And that's the mod argument form, or it's often called the polar form of z. And you can see on that full working the importance of sketching Z to make sure you get the correct angle, and that you can see the correction there of the extra plus pi added to the minus pi by 3. In the next session we're going to be looking at converting the modulus argument to Cartesian form.